Thank you, Ed. Good morning, everyone. It's Clyde Graham. I'm Executive Vice President at Fertilizer Canada, and I'm pleased to introduce the third in our webinar series on Canada-Africa 4R Solution and Precision Nutrient Management, presented by the University Mohammed VI, Polytechnique, and the University of Manitoba. Today's session is going to be on the effects of 4Rs on greenhouse gas emissions. The online series is brought to you by 4R Solution, University of Manitoba, and Mohammed VI Polytechnic University, with sponsorship from OCP North America. 4R Solution is a Global Affairs Canada funded project that is working to improve socioeconomic well-being and resilience of 80,000 smallholder farmers, particularly women, in Ethiopia, Ghana, and Senegal. It is a public-private partnership. The series aims to create a network of African and Canadian scientists and academics with a goal of advancing 4R and precision agriculture science and extension. The event was originally planned for a 3-day event in person at the University of Manitoba, but due to COVID-19, the program was postponed and has now been redesigned into 8 2-hour sessions. And I said this is the third of those 8 sessions. At the heart of our program is 4R nutrient stewardship. 4R nutrient stewardship can help grow crops sustainably, and the 4Rs work to increase production and profitability for farmers while ensuring the future of the agricultural industry. It's based on the concepts of the right source of fertilizer at the right rate, the right time, and the right place. And I want to thank our sponsors and partners from Canada and the United States, or Canada and Africa. And now I'd like to introduce our webinar moderator, Ed Reggae, the founder and CEO of ECI Africa and Emerge Africa. We're thrilled to have Ed, who has over 35 years experience in agriculture and worked at many different functions. So I'll turn that over to you now, Ed. And just note that we understand that the slides are a little grainy, difficult to see. We are working to see if we can try and correct that, but I would note that all the slides will be available on our website at the end of the program. Ed, over to you.
Okay, thank you. Thank you. So we have 4 presenters today. After Clyde's introduction, the next presenter is going to be Claudia Wagner, and all of the presenters, you have their bios. So if you go to the site and click, you will see their bios. We won't spend time introducing them. After Claudia, we'll go to Mario Tenuta, and then we'll have Job Kihara, and finally Kaushik Manyugdar. I would like to just remind you that in addition to the slide deck being on the web, we also have, we will use chat room to ask questions, and the questions will be answered in detail later and be posted. So some will be sampled and answered during the call, during the webinar. Others will be available in detail. Other responses will be available in detail later. So I would like to, at this point, to now invite Claudia to present her work, which is focusing on the 4R effects on total GHG emission in Western Canada. Over to you, Claudia. Oh, sorry.
Eastern.
I read the wrong one. 4R effects total GHG emission in Eastern Canada.
Yes. No. Thank you very much, Ed, for the introduction. Okay. So next slide, please. I'm going to start with just a little bit of an introduction on greenhouse gas emissions, what the sources are, and then move on to some case studies, some of our results on 4R and their impact. So greenhouse gas sources of importance are enteric fermentation and manure, either stored or in pasture, and those emit methane. But also manure is also a source of N2O, but the source that I'll be talking about the most are soils as a source of nitrous oxide. Depicted here too, we see the CO2 arrows going in two directions, meaning that agricultural systems can be either sinks or sources of carbon. And later today, we will hear from one of the speakers, Job, about the carbon impacts and that link to the nitrogen emissions. But I will focus on the nitrous oxide. Shown here are also emissions from energy, which tend to not be compatibilized in the agricultural emissions. And then also very importantly, the CO2 emissions from land use change, which again, I think are going to be referred to perhaps later on. So if we look at the world overall in the next slide, you will see that the contribution in North America, and which is the third bar down, you probably have a bit of trouble reading that, and Africa, which is the second from the bottom, they're approximately, they're not that different. But if we look at the distribution of what these sources are, next slide, and you will not be able to read that at all. You will see that, so the third from the top is North America, and the second from the bottom, Africa. And the yellow areas are those sources of nitrous oxide from soil. Particularly the light yellow is the source from fertilizer nitrogen. So you see a big difference, much higher proportion of—
Claudia, sorry, I would like to suggest that we use your slide deck. I think it's really difficult.
Yeah, it's
I think we need to shift to your slide deck, and if Labonia can give you the screen share possibility.
Okay. Yeah, I'm ready to go.
Slides.
Yeah.
Because we are not following.
Yeah. Okay, I think if we just want to pause for 1 second, we'll try and reload the slides. So if just everyone bear with us for 1 second, we'll try and, your screen will go blank and then we'll just try to reset, okay?
Thank you. Sorry, Claudia. Yeah.
Okay, no problem. So maybe I'll just pick up on this slide here, which you now can see from the third from the top, North America, and the second from the bottom, Africa. So what I was conveying before was that the emissions are not that different a little bit, but the real difference is what you see in the next slide, which is the distribution of sources. So while in Africa we have a big prevalence of emissions from pasture. Next slide, please. Which is shown there in the light green. So manure deposited on pasture, emitting mostly nitrous oxide. What you see in North America is the light colored yellow. Synthetic fertilizer is the largest contribution when we look at emissions from soils. And those are all in the form of nitrous oxide. So what I think a large portion of this collaboration is about is that we know to increase yields or to close the gap yield, better plant nutrition is needed in Africa in general. And with that, there's potential to increase that light yellow bar there to be a much lighter proportion. And with that, the overall emissions will also increase. So in the next slide, we see that for Canada, so it's a snapshot of Canada here. And in the eastern part includes Ontario and Quebec and the maritime provinces. And what we see in Eastern Canada, it is a hotspot for intensity, even though the overall emissions are not as large as in the West. So you will get the Western perspective from Mario Tenuta, and I will concentrate on the Eastern Canada part, which is a humid region, and therefore the intensity is a lot higher, which you will see in a minute of why that's the case. So in the next slide, we are just zooming into that circle in Ontario, where we have a lot of corn production. It's the main area, and corn, as we know, has one of the highest nitrogen requirement among major grain crops. And the nitrogen use efficiency is relatively low. So the point of using 4R practices is to improve that efficiency and decrease the losses of nitrogen to both water and air. And of course, I'm in this talk concentrating on air in terms of greenhouse gas emissions. So the next slide gives us an idea of, for the whole of corn production now expressed in terms of greenhouse gas emissions per ton of grain or megagram of grain. We see the proportion of soil nitrous oxide is the largest, larger than 50%. So the blue pie piece here in the chart. Synthetic fertilizer production about 13%, and then this is applicable to Ontario. Grain drying, where a lot of fossil fuel is used, is another proportion. So it's important to then manage that 56% of emissions and try to reduce those as much as possible. In the next slide, you will see that this soil nitrous oxide is of microbial origin. Both the nitrification and denitrification process result in N2O emissions. This diagram has been dubbed or called the hole in the pipe model, in the sense that we have nitrification, so ammonium producing nitrate, so this flow through the pipe occurs. But then there is a hole in the pipe through which N2O escapes. So it's kind of a byproduct. And then in denitrification, from nitrate to all the way reduction to N2, the same occurs. That N2O then diffuses out of the soil. And what I want to point out that any nitrogen addition to the soil, be it synthetic fertilizer or animal manure or legumes, will increase the organic N levels, but also ammonium or nitrate, depending on the source. And with that, they will increase the flow through the pipe. And then there are also processes or conditions in the soil that increase the hole in the pipe, so to speak. And in the case of denitrification, when we have low oxygen, high water content, that's when we get the highest emissions of N2O. So the next slide will show you an example of some of our measurements. I've removed numbers on the y-axis. It's not relevant right now, but basically, if we look at days after planting, and the picture shows fertilizer being applied, so at day 0, so right at planting. And for a while, not much happens, but then when we get rain, we get these peaks of emissions. So we talk about nitrous oxide being produced in hot spots and hot moments. So hot moments means things converging in time, meaning the ideal conditions resulting in N2O production in the soil and then emission. And hot spots because where the fertilizer is, for example, if you apply it through injection in one spot in the soil, that will be a hot spot of N2O production. So a lot of spatial variability. It's important to understand these processes because when developing the 4Rs locally, it's really about managing those hot spots and hot moments. So the next slide, I think, just gives you an overview of the 4Rs, which Clyde already showed this slide. In our case, the examples that I will show are for right source, right rate, and right time. And as I just mentioned, these knowing what the right source is or what the right rate is requires local research to develop these practices because they're very specific to the conditions where the fertilizer is used. So in the next slide, we get an overview of the effect of timing, for example. In our case, this would be either applying at planting or at something like between the 6th or 8th leaf stage in corn. And this is the time just before the fast uptake occurs. So the idea would be that this would minimize losses. What you will see that in our case, it's a little bit hit and miss. Sometimes we saw effective results, sometimes not, very weather dependent. In the next slide, you will see some pictures of measurements done back in 2011, 2012 by my PhD student, Amal Roy. And it also gives you a glimpse of the equipment that we use for this. So in this case, it's a chamber, a static chamber where samples are taken manually, and it covers the whole of the inter row or between rows, so that emissions are captured and we don't have that high spatial variability. So in the next slide, you will see some of the results of those studies. So in red, 2011, in the hatched columns, 2012. So, and these are total N2O emissions measured over the study period, so in kilograms of nitrogen per hectare. So first of all, you see large differences between the 2 years, and that has to do with the weather. So 2012 was very dry, we got minimal emissions. Secondly, you will see that on your left, you see the results for planting, and on your right, the results for the timing at the V8 stage. So the black arrows depict that 145 kilograms applied at planting had much higher emissions than 145 applied at the V8 stage, and the same thing for the 218 kilograms. And the other thing that we see here is the rate effect. So a rate closer to the optimum the plant needs, so 145, is much more effective in terms of reducing the nitrous oxide emissions. So here's an example of what the right rate and the right time would be in this particular case. Next slide shows part of another aspect that we've looked into, which is the right source. So EEF stands for Enhanced Efficiency Fertilizer, and that is a urea where 2 inhibitors have been added, both urease to decrease ammonia volatilization, and a nitrification inhibitor to block that ammonium to nitrate production. So keeps the nitrogen and ammonium form to reduce losses in terms of nitrate leaching and or denitrification. So a question we had was, using this enhanced efficiency fertilizer could delay the nitrogen release and also then decrease losses. So next slide. So the experiment that we've conducted is shown here. And I want to focus your attention to the left side first. So with nitrogen applied at planting, having both urea or enhanced efficiency fertilizer urea, that comparison, so that would be our right source. And the next comparison on the right, having nitrogen applied at side dress, either in urea ammonium nitrate form by itself, or UAN with this enhanced efficiency or with these inhibitors, both the urease and nitrification inhibitor. And the cross arrow there shows a comparison that we wanted to do, which is urea with the inhibitors applied at planting. Does that act like delaying the fertilization? Because there are a lot of advantages of applying the fertilizer at planting and not having to go in again later on. Next slide. So this was conducted at sort of a field scale with a method that is not that commonly used. What you see in the middle there is a depiction of where the position of a trailer where we had all of our instrumentation. And those black lines are tubing that gets directs gas to the trailer where it gets analyzed. Next slide shows some of the equipment that we have in the trailer and out in the field. So it basically is a technique that relies on gas sampling from two heights. The air gets sampled both in the upper and the lower position. And then we use turbulent theory to calculate what the emissions are that are coming from the soil. The advantage is that we can integrate emissions over a large area. So we avoid those hot spots, and also we get good temporal resolution, as you saw in the slides that I showed before. Next slide shows some of that temporal resolution again. And if you recall the similar slide that I showed before, we had the arrow of nitrogen application at 0 days, so it was applied at planting. This is the plot where, or the results for the plot where the nitrogen was applied about 40 days after planting at this V8 stage of vegetative stage of corn. This plot did not get the peaks earlier on with the big rain because there was not enough or excess nitrogen in the soil. However, when the rain came right after, it had emissions again. So in this case, the right timing only shifted the peaks, but didn't show a reduction. But I see potential here, which is if we adjust the rate, because at that point you perhaps can assess better the rate needs for a good production, then there is potential for adjustment. So combining two of the 4 R's, the timing and the rate adjustment potentially. Next slide. This gives an overall results from that study. So the first thing that I want to point out, so over the 3 years, if you look at the black bars, 2015, no significant difference, but 16, a small reduction. Emissions were low because of dry weather, and big reduction in 2017. So 2 out of the 3 years, the black bars show the effect of the use of the inhibitor in reducing emissions. They were effective 2 out of the 3 years. For the green bars, we see for the nitrogen, nitrification and urease inhibitor used with UAN, which is the urea ammonium nitrate, was effective in 2015 and 17, but not in 2016. So 2 out of the 3 years, we had an impact of right source. For timing, we didn't see an effect. And we also didn't see an effect of that comparison that I was talking about, which was applying the nitrification and urease inhibitor at planting versus compared a straight no inhibitor later on at the V8 stage. So next slide gives just some general concluding remarks. So we, in our area, see the highest N2O emissions when we have nitrogen fertilizer at planting, when soil moisture is relatively high and the corn N uptake is low. But we can also see these emissions a bit later on if there are higher rainfalls. Something I didn't talk about, but I wanted to mention is that in that study where we looked at the rate, the highest rate had only increased grain yield by 6%, but the N2O emissions by 64%. So very important using the right N rate. And the nitrification and urease inhibitors that we looked at reduced N2O emissions in 2 out of the 3 years. And I think we can try to manage those hot spots and hot moments by combining a number of for our practices, for example, timing, use of inhibitors, reducing rate, perhaps placement as well. I think you will be hearing about that from Mario. So my next slide just shows you a nice crop of corn in Ontario and my contact information. And the last slide is just an acknowledgement to funding we've received and the technical support from my technician and postdoc and the graduate students that actually have done all this work that I'm talking about today. Thank you.
Thank you so much, Claudia. I know, I mean, you are time pressure because of the slow start, but you pulled it off. Thank you so much. I appreciate. I would like to make a proposal to all of us that we listen to Claudia so that we have both Eastern and Western Canada together and have the conversation. In the meantime, request Shami to start to just compile them together. However, I would like to, because Shemi has been looking at the questions, if there is one that is really about clarification, then we can zoom into that quickly before we move to Mario.
Thanks, Ed. I think we have one question in relation to the methods for assessing nitrous gas emissions. Claudia, if you could probably briefly explain the processes and the concept of how the gaseous losses are measured from the field.
Okay, so I showed pictures of two methods that we use. The first one is really just a box that you put over the soil. I mean, it's not as easy as that, but if we imagine these gases coming out of the soil as they are produced, if we cover the soil and wait for a certain period of time and sample the headspace, then we can get we can infer how much was emitted by the increase in concentration over time and by taking samples at 10, 20, 30, or 40 minutes. And the other method is a little bit more elaborate and requires a lot of expensive equipment, but that involves sampling at two heights, and the difference in concentration in those two heights used with what we call a turbulent eddy diffusivity allows us to calculate the flux.
All right, thank you so much, Ed. I think we can proceed to Mario's presentation. A lot of the questions that are here would be very relevant for the two presentations.
Thank you. Yeah, so Claudia, stand by. We'll have a combined set of questions that includes Mario's. I can see Mario is ready to go. Mario, over to you, please. We are now in Western Canada.
Thank you, Ed. Thank you, Claudia, for setting excellent background and information that I can build on in this presentation in Western Canada. So I am the 4R Senior Industrial Research Chair for Canada at the University of Manitoba. And pleased to be with you today to talk about our experience in Western Canada in terms of reducing N2O emissions and with use of 4Rs. Next slide, please. So where are we? So basically the Canadian prairies with that arrow is the bulk of the emissions for nitrous oxide. And you can see it's quite a large area. I believe that's about the size of Nigeria, okay? And then in the eastern side where Claudia was just speaking about is much smaller. I think it's about the size of Ghana, and but very different production systems and environments which the gases in agriculture can be produced. Next slide, please. Okay, our soils are very young. So are the soils in Eastern Canada, because as the image on the top left shows, there was a big chunk of ice, a big ice cube, as I like to say, above most of Canada. And that really set the stage once it melted for young soils. And our soils here on the prairies were formed on grassland. And for much of that time, for at least for several thousand years, it was bison, or some people call buffalo, that were grazing that grassland. So we have grassland soils, and as a result of that, our soils under the FAO system are mainly Chernozem, Castanozem, Vertisol, Fluvisol, and Luvasol. Luvasols are more towards the north where we have trees, where we grade into trees in northern Canada. And these soils are very deep in terms of the deposition of the soil after the glaciers. They're relatively flat for most places in the world. They're mainly semi-arid, which is a key difference than Eastern Canada, drier, except for my area where I come from, which is the easternmost portion of the prairies. That is basically subhumid area. We produce only one crop a year between May and September, which is quite different than the situation in Africa. And on the right there, you can see a profile of a Chernozem where the A horizon is dark with organic matter from that grassland, a legacy. And that depth of that could be 50 centimeters, even 60 centimeters, that A horizon in some cases. So we're quite blessed with a really good starting point in soils here. And next slide, please. And we also have the winter, as I said, outside of May to September, we're not able really to grow too much in terms of for a crop. And you can see on the top right, there's snow often covering, and we have ice on one of our sampling lines, a similar system to what Claudia has. You can see the icicles hanging down. You can also see the beautiful black soil in which we study on. Beautiful crop productivity in the bottom left. You can see there canola and wheat growing and slightly rolling hills. And on the right, again, you can see that flat soil. And you can see forever. Okay, it's wonderful. Next slide, please. And because of that, we have a great degree of mechanization in our soils. Here's an example of the largest harvest at one time in the world, or fastest harvest of a field in the world. With I don't know how many combines are in there at the same time. The bottom right is a seeding operation with anhydrous ammonia 8200 going on at the same time in the very early spring. It looks like there's still some frost on that stubble. Okay, that's the degree that we're looking at here, and it's mechanized, which really lends itself well for our practices, particularly in terms of the timing, source, well, all the 4 R's. Okay, and our area is quite diverse. One of the most diverse cropping in terms of export cropping places in the world. Where wheat, canola, lentil, dry pea, edible bean, chickpea, potato were major exporters of these crops, and then for livestock, beef and pork. Next slide, please. Okay, so Claudia showed you a slide, and our intensities are a lot less in terms of N2O emissions than in Eastern Canada. And because of that, our actual overall emissions, as in the bottom right pie there, in the blue for Western Canada, is actually lower than that of Eastern Canada, despite the fact that we have several times more land area that is cropped. Okay, and that comes down to a few factors. One of them is that our area is drier. Like I said, semi-arid to subhumid environment. We also have very cold winters that the soils don't do very much in terms of biological activity over the winter because they're solidly frozen. It can go frozen up to 1 meter in depth. And also the crops, we don't have corn growing over all that region. There's only a small area that can grow corn in my area. And so the crops grown other places don't require as much nitrogen. So we're using per area a bit less nitrogen than in the east. So I'm kind of giving you a situation where we're coming from here. Next slide, please. So nitrogen cycle, what we're looking particularly at here is a nitrogen fertilizer added here as an example of 4600 added urea, which would be liberated to the ammonium form and then can undergo nitrification to nitrate, be taken up by crops and so forth. Next slide, please. And here are the two spots where N2O can be produced. So Claudia showed this as the leaky pipe framework or model. And here I'm showing it as part of the nitrogen cycle where denitrification, so the loss of nitrate via reduction by bacteria under wet conditions promotes N2O emission, and then secondly, nitrification in the process of ammonium being converted to nitrate by bacteria in soil, which is natural. And actually, we need it for crop production to produce nitrate because then the crops can take up the nitrate readily. And we find it's really that nitrification source is the most important in terms of N2O emissions. So when we're looking at 4Rs, that reducing that nitrification source is very important. That's not to say that denitrification is not important. That seems to be very important in the springtime when the soil becomes thawed, or when it goes from being frozen to melted. That's when that denitrification becomes a significant source of N2O in our soils. Those are the two things that we are targeting with the 4Rs in terms of reducing N2O emissions. Next slide, please. Now, it's not that simple. I wish it was simpler, but we have indirect means of N2O emissions, and there are two dominant sources of this. One is the loss of ammonia. So a fertilizer like urea, if we place it at the surface, or even manure deposition, or a paddy or urination spot on the surface of soil can result in ammonia, NH3 volatilization. This NH3 is not a greenhouse gas on its own, but in the atmosphere, particularly high up in the atmosphere, it can be converted to N2O. So we refer to that as an indirect means. So we have to consider this because it can be very significant in terms of a source of N2O emissions. The other is nitrate leaching, where the nitrate can be denitrified in water, lakes, rivers, even groundwater, and there produce N2O via denitrification. So I'm going to talk a bit today about the ammonia volatilization, which is particularly important with fertilizer. Not to say the nitrate leaching is not important, of course. It's just that in our area, it's only on the sandy soils that becomes important. So keep in mind, we have direct and indirect means of N2O emissions, and for our practices can help us reduce both of them. Next slide, please. So here's an example with potato that looking at the rate in the 4R, and that as the rate of nitrogen fertilizer goes up, the emissions of N2O also go up. In this case, it's linear, and we tend to find this when we study from May to September, our growing season. We see a linear increase in fertilizer, in N2O release with fertilizer rate. Next slide. However, when we look at the whole year with a method similar to what Claudia showed in terms of a micromet flux gradient approach, which measures from January through December all year, when we add in that non-growing season, we can see that we get more of an exponential increase with higher rates. And that tends to be because we also get these spring thaw emissions that are really accentuated with high nitrogen rates. And at these high nitrogen rates, to the right above 150 kilograms of nitrogen per hectare, we're talking about growing corn because it really requires that much nitrogen, as you know. And so it is very interesting that it's different. A lot of our studies look at growing season only emissions, but because of this availability of specialized methodology, we're able to look at the whole season emissions, and here it's exponential. And others have also shown exponential increases in response of N2O to nitrogen rate when looking at the whole season. So rate is one of the most important aspects to control N2O emission. I think that's very obviously clear here, and particularly when we're talking about at the high rates. Claudia showed this as well in her presentation just now. Next slide, please. So Claudia showed about enhanced efficiency fertilizers. These are fertilizer products now that are kind of like the next generation of fertilizers, and they're high-tech fertilizers, smart fertilizers, something like people call them by different names. Okay, it's a fertilizer by formulation that improves the uptake of nutrients it contains by the crops. Okay, so it should be more efficient in terms of as a source of nutrition. Okay, may reduce losses of the nutrient to the environment. In other words, we get more of it into the crop than and less to the environment or loss. That should be a good thing. May alter the timing of availability of the nutrient to when a crop needs it. So we can modify the availability, the timing of the availability by when we apply the product. But with some of these fertilizers, they have built into them the ability to release the nitrogen over time, not just as a slug at planting, okay? And in some cases, it can be much easier for the crops to take up in terms of keeping the nitrogen close by the rooting zone, rooting area as well. So enhanced efficiency fertilizers, this is a big component of North American agriculture now, and a very large growth area. Now, this is probably going to cascade into Africa within this coming decade. Next slide, please. So what are these enhanced efficiency fertilizers? Well, there's several groupings. Categorize them into three classes. There's the stabilized nitrogen, and these which have an additive to them, an inhibitor. Usually it's an inhibitor of enzymatic processes of bacteria. So we have on the market various urease inhibitors. So this prevents urea from forming ammonia quickly. So reduces volatilization losses. Very good for surface applied products. Nitrification inhibitor that reduces or slows down the rate of transformation of ammonium to nitrate. And these I'll show you, and Claudia showed as well, really are effective in reducing N2O emissions. And some products are double inhibitors, which have the both products together. And Claudia showed as well a product, Super U, that has this as well. Now on the right there, that image is a polymer-coated urea. And this is a thin plastic polymer, very thin, surrounding the conventional urea granule. And that plastic is enough of a barrier to slow the release of the urea to the soil solution around it. And now the release is dependent on temperature and moisture. So it's a really interesting product because now the soil conditions will help determine the release of the nitrogen. So it's really good in sustaining a longer input of the nitrogen from the granule rather than one big shot at planting, because as you know, urea is very soluble, and then hydrolysis of the urea and nitrification be fast. The third class is slow release nitrogen, which have been around for quite a while, some of these. And these are just by modifying the formulation and make it tough for bacteria and their enzymes to chemically break up and release the nitrogen from those products. These are not as used as much as the stabilized and the controlled release end products. So these are going to be coming your way and in Africa. And also keep in mind that this is just the first generation. We're going to have even smarter fertilizers coming down the pipeline. Next, please. Okay, so here is an example of Broadcast Incorporated. fertilizer products, ESN, the polymer coated urea in green, and in purple, the Super U, which is a nitrification urease inhibitor, in the purple. And the red is just conventional urea. And you can see that after the N is applied, and we got a rainfall then, just after that, the urea is producing more N2O emissions than these enhanced efficiency fertilizers. That's pretty neat. So they're here, and it's a very clear case of a reduction in N2O emissions. And you can see there's not much happening after that period. Even the checks are bouncing up and higher than the fertilizer treatments due to rainfalls that have occurred later on and after harvest. But it's that period after the fertilizer's addition in the spring where these products are working. This is with corn. Next slide, please. Here's nitrification inhibitors, an example of them working with wheat, spring wheat. In the red box is Super U, so that's a double inhibitor, including a nitrification inhibitor, a DCD, and Entrench, which is only a nitrification inhibitor that contains nitropyrin. And these are, I forget now, 10 site years, mostly in Manitoba, but some in Saskatchewan. And you can see that these inhibitor products really work to reduce N2O emissions in various indices or ways of summarizing N2O emissions relative to yield and area. And that emission reduction is anywhere from 1/3 to 1/2. Very significant. Next slide, please. And now looking at in-season application, this is back to corn. And up front, we added a partial N applied. So we call that, with a starter fertilizer in terms of nitrogen applied. Not much emissions, but there's not enough there to really crank up nitrification and get N2O emissions happening. That same as what Claudia showed in the east. But when we apply the rest, about 60% of the nitrogen that's required by the crop later on, for us, it's around the V4 stage. And then you can see, and followed by rainfall, you can see that spike in season. And in this case, the UAN, which is urea ammonium nitrate fertilizer, 2800 liquid that our farmers like to use in season, you can see it being the highest on the top panel. And then followed by the urease inhibitor with that UAN that doesn't have any reduction on N2O, which makes sense. But when the nitrification inhibitor is added, that's the light blue, it drops down quite a bit. So it works, these nitrification inhibitors work in season as well, similar to what Claudia showed. And then at the bottom panel is how we can manage how we add this liquid fertilizer in season. Either dribble banded on the surface, shallow side dress, which means putting it next to this crop row under the soil about 3 to 4 centimeters, okay? And here you can see that as we bury that UAN, the 2800, we get less emissions. So we can use a combination of placement of the fertilizer and even nitrification inhibitors if we really wanted to even capitalize on more of an N2O reduction where we can compound the benefits for our practices. Next slide, please. And here again, looking at placement options where we have on the left, urea, incorporated broadcasted, producing the highest N2O emissions over time. Those are cumulative emissions shown. But with the S, urea S is sideband, which means put it narrow band next to the crop row, about 3 centimeters deep, less N2O emissions. And then if we put the urea below ground every second row, but between rows, and as we call it mid-row banding, we get even lower N2O emissions. And then when we add, when the source is not just urea, it's actually ESN or the double inhibitor product Super U, we get even more reduction. So again, showing this compounding effect of placement with source. That was a wet year. In a dry year on the right, we still get the same pattern, but not as accentuated in terms of the benefit. Next slide, please. Now, just switching to ammonia, I'm going to skip over this slide pretty fast here. It's just showing you the the process in which ammonia is volatilized from surface placed urea. Next slide, please. And here's the benefit of these products and placement to reducing ammonia emissions. Ammonia emissions can be very significant agronomically. We could be losing 5, 10, 15, 20 kilograms of nitrogen per hectare, which is important for a farmer, by surface placed urea. And you can see here the surface urea addition, the greatest cumulative losses. It happens the most after the first 2-3 weeks of addition. The inhibitor product with urease inhibitor to Super U, less emissions immediately after application. And then when we shallow place the Super U or urea, in other words, get it at least 3 centimeters into the soil, much less volatilization. And when we deep band it at about 10 centimeters, actually as much as we get ammonia volatilization reduced to that of as if we added no nitrogen to the soil. So we can use, again, the source to control if we have to put it on the surface, which some of our farmers have to because of the crop or the timing, the soil conditions in terms of moisture and so forth. But also because of our mechanization, we can use, we can place it at various depths, which will control the ammonia as well. So various options for farmers, which is very exciting. Next slide, please. And this is in season with the UAN, the 2800. And similar thing, if we, with the sources, if we add Agrotane Plus, which has a urease inhibitor and nitrification inhibitor, we get a reduction in ammonia volatilization. If we add just a urease inhibitor, we get much better reduction. And I think that's because the nitrification inhibitor can actually back up the nitrogen cycle to allow for some more ammonia to be emitted over time. So in this case, to reduce ammonia emissions with surface supply, just put the urease inhibitor on. That gives you your best bang. Next slide. So conclusions, using 4Rs can reduce direct and indirect emissions of N2O in Western Canada. I haven't shown you the leaching benefits because we're just getting into that. I think Claudia has some data on that. Reductions are between 30 and 50%. So the reductions won't happen every year, but we average out in terms of similar to every 2-3 years. So we're hovering on average, if you go over years, about at least 30 to 40% when we average out. That is impressive. Widespread adoption of 4R practices in Western Canada may reduce total N2O emissions from our agriculture between 15 and 25%. That is incredibly significant compared to other options that we have that are practical. So lots of benefit and potential for using 4Rs for sure in Canada. And I'm quite sure in Africa as well, it's going to need to be thought of differently because your conditions are way different than mine here in Western Canada. But I'm pretty confident that there's going to be great benefits. Next slide, please. So I'd just like to, there's lots of people to thank. I can't go through them all, but you see some action shots here. Please, if you use Twitter, follow us at Soil Ecology UMan, or visit our website at www.soilecology.ca for more information on our projects and on our 4R Senior Industrial Research Chair. With that, thank you very much.
Thanks, Mario. Thank you so much. I would like to try and use as many minutes as possible to get some questions on the table. Shami, are you ready?
Yes, Ed.
Some rapidly, yeah, thank you.
Yeah, thank you so much. I think we have a series of very insightful questions. Mario, if I could just start with you. You did indicate that there are some aspects of leaching that you are addressing. There's a question here about the specific role of 4Rs in reducing leaching, in addition to reducing the gaseous losses as well. Can you just briefly provide the scope of 4Rs and some of the technologies on that we have addressed today on reducing leaching losses?
Sure, Shami. So it's a good question. So I kind of look at it as there's two opportunities to reduce N2O emissions and also just in general nitrate leaching. The first is in our environment here in Eastern and Western Canada, in that if we apply nitrogen upfront at planting or just before planting, there's an opportunity for loss of that nitrogen before the crop really kicks in to take up nitrogen. Okay, so what, because the nitrification by the bacteria in soil happens much sooner than crop growth. So you can have nitrate build up from the fertilizer application at planting, the plant not taking it up. Then what happens if you get a big rainfall and you're on a light texture to sand soil? Well, that nitrate can percolate down through the soil and be lost. So by using 4Rs, we can reduce that risk, either by altering the timing to in-season application, if you're fortunate with a long growing season crop, like corn or potato. But if it's a short season crop, then we can use something like a polymer coated urea or nitrification inhibitor products to delay the production of nitrate to when the crop is really emerged and taking up nitrogen. That will reduce nitrate leaching for that pre-growing season period. And then the other is with 4Rs in general, by using all the 4Rs, to reduce the carryover, or what we refer to as residual nitrate after harvest. So in Eastern Canada, it's more humid. In my area, it's subhumid. Well, we can get leaching losses before the soil freezes. And in Eastern Canada, the soil may never freeze. So that's a good period for nitrate to be percolated down through the soil and lost, okay? So by using 4Rs, we can just, in general, reduce the residual nitrates as well. So there's two benefits to using 4Rs in reducing the leaching.
Thank you so much. Claudia, there's been a lot of interest, several questions asking about the role of modeling in estimating nitrous oxide losses from the soil. And then also if you could shed some light on the utility or any existing models that are available, or the options of strengthening the capacity of existing crop soil models like DSAT and STIX to measure nitrogen emissions from the soil.
Yeah, great, thank you. So I think as far as I'm aware, DSAT, the crop models themselves don't have the N2O subroutines, but I think they can be coupled to other models like STIX. One of the questions was related to that. So that is a model that does predict the nitrous oxide emissions. There's also DNDC and DayCent, which we have worked with. So my view on this is that we have to always be careful with models. So they need to be obviously validated and calibrated for the region. So they don't replace having data. So you need good data. What you can do with models, which we have done in a number of studies, is to predict emissions over a longer period. So just giving us as an example, the timing study that I showed. We had an effect in 1 year, we didn't have an effect in another year. So then the question becomes, what if this is the probability of the results being like the year where you had a reduction versus the year you didn't have a reduction? And you can get to that question by running the model over 30 years and then evaluating what is the probability. Do we see an impact of timing or not? So I think they can really augment our knowledge or understanding of the processes, but they don't replace the data.
All right, thanks so much. Then Mario, briefly, if you could address the issue of cost-benefit analysis. We did mention mostly the role of the different 4Rs and enhanced efficiency fertilizers on reducing gaseous losses. But have you conducted the economic analysis of the benefits that can be derived from the interventions?
Yes, we have done some preliminary cost benefit analysis now with particularly with the different sources of nitrogen fertilizer. We do not see a big boost in yield. Okay, what we're doing now is fine-tuning the rate estimates for a crop based on using 4Rs. So most of our research has been done at the recommended nitrogen rate, and then those have been showing not much of a benefit in terms of yield. And having looked at that, it makes sense that's not showing a benefit because the rates are always set to be a bit higher than likely needed for an individual field, because the rates are designed for averaging out over a large area of different fields. So what we've done now is looking at doing end response curves with 4Rs. And that is showing that we're going to be able to fine tune if it's a 5 kilogram reduction in nitrogen application rate because of the products, then we're able to see that now. So our cost benefit analysis is going to get better because of that, okay? But I can tell you right now, these products are more expensive, okay? There is a premium associated with them, okay? And it's about anywhere between 5 and 15%, depending on the product and the time of year and where you're buying it, in terms of extra costs compared to, let's say, conventional urea fertilizer, okay? So that can be considerable, you would think about that. But if it allows a farmer to put on their product and more conveniently, such as at planting or pre-plant, such as the case with the polymer coated, that improved convenience may be worth it for that farmer, okay? Because we're highly mechanized and our farmers have large areas and they only have a short window to get their stuff done. So it allows them to get their stuff done. They love that, okay? And they'll pay for that. And also, if it allows them to put the fertilizer in the fall and stay in the soil over the winter, because in the fall they have more time to be able to put fertilizer down, they'll pay for that as well, okay? So it's tough to do a cost benefit because there are some things in there that the benefit that can't be monetized, okay? Especially the convenience of being able to, and the change in the operation system of when things get done. And that's really important in our systems because they're very complex mechanized systems. So at the moment, I would say that if you did a conventional cost benefit analysis, it wouldn't be that great. But that doesn't really reflect the reality to the farmer, okay? The other aspect is there is no benefit in terms of cost, in terms of monetary benefit to the farmer by reducing N2O at the moment in our cost benefit analysis. If the farmer is paid on let's say on an international market for greenhouse gas credits for reduction in N2O, that's going to start to change the situation. So some of our preliminary work was saying that the N2O emission reductions on current market value for carbon can compensate for about 15% of the cost of the fertilizer, of the enhanced efficiency fertilizer. That's a start. And keep in mind, the value of that carbon is very low at the moment, okay? That's it.
All right, thanks so much, Mario. Unfortunately, we have run short of time for this Q&A session. Several very insightful and important questions that are going to be answered following this webinar and by written responses, and we will be we have due diligence. We have all the responses provided, but there are several questions relating to the opportunities for some of the technologies in Africa, as well as potential for collaboration that we may bring at the end of the webinar if we manage to save some time as well. Ed, back to you.
Thank you so much, Shemi. So, ladies and gentlemen, we'd like now to shift to two presentations which focus very explicitly on Africa. The first one is to be presented by Job Kihara, who works for SIAT, and the last one will be presented by Kaushik, who works for Africa Plant Nutrition Institute, APNI. So, Job, are you ready?
Yes.
Over to you.
Thank you very much, Eddie and Shami and all the other organizers of this meeting. I want to start by introducing the agricultural work and research in Southern Africa. In general, there are probably several differences with other parts of the world, including Canada. And one of those differences is that farmers have small land holdings of less than 1 hectare, and they mostly do mixed farming. That means they keep livestock and also they grow crops. The other difference is that the penetration of mechanization is not as high as in other parts of the world. So much of the work is done using hand hoes and manual labor. And the third difference is that the rates of input use are quite low, generally less than 20 kilograms of fertilizer, NPK, per hectare. As a result of this, the yields are themselves quite low. For cereals such as maize, wheat, rice, sorghum, millet, the overall yields are less than 2 tons per hectare. And in the work that was done by ITASUM in 2016, I think, they did show that that level of yield can actually be increased by another 11 tons per hectare in some of the places. These are huge increases that show the potential that can be harnessed with good practices that also help to observe a clean environment. Next. The observed productivity is driven mostly by carbon. And here, there are 3 issues that I want to bring out. Carbon is influenced, and both also productivity, by the frequency with which farmers apply manure in their plots. This is also driven by the positions of specific fields within the landscape, because this determines erosion and depositions. Another important consideration is proximity of specific field portions to the homestead. Those fields that are closer to the homestead, and that's what the partition tree is showing there, have higher productivity than fields that are further away from the homestead. And these are important for guiding site-specific nutrient management, because the context here is quite different than what has just been shown for Canada, where the lands are quite heterogeneous. And this is important for us to make decisions on managing of fertilizers. Next. Yeah, soil organic carbon and fertility levels are also influenced by transfers of organic resources between households within a community. Those transfers are because of exchanges that people within a community would require, for example, services of transport or help with plowing, and because of such services, farmers would give organic resources in exchange. And from that, we find 2 results. Those farmers who are net importers of organic resources such as manure and crop residues obtain an increased harvest from their fields compared to those farmers who are net exporters of such organic residues. Secondly, we also find that those fields where livestock actually feed within the fields and make their droppings within such fields also produce higher yields than fields where organic resources have to be taken out of the field. So these various proxies of carbon provide useful information for guiding nutrient management. Next. Yeah, because of the resulting differences in this type of landscapes, what we find is that the responses to fertilizers applied and nutrients are quite varied. If you look at the figure, the bar graph there shows response to two sources of fertilizer, basically two sources of phosphorus. That's the ammonium phosphate and local fertilizer in Tanzania, which is called Mijingu Mazao. You can see clearly that there is a good response to of the crop when you compare that with the control. But when that is decomposed to consider the various locations where these are coming from, some places have negative yield compared to the control. If you look at the cumulative plot, the broken line shows the yield of the control at 0, and the differences is because of the management practices. So, and the location of the field. So some of those fields where the improved practice, which is a practice involving application of fertilizers, is still achieving lower yields than the control plot, shows that those fields are actually wasting fertilizers. But we also see some fields where there are some good responses. When those are averaged, we don't see those differences, we just see some increments. But breaking it down like this and understanding that there are variations because of the heterogeneous fields in which farmers operate, help us to be able to target nutrients. We also see the effect of season in terms of differences in the way the responses occur, and it's important also to consider such, and being able to advise farmers on what to apply, which season, and where is important for us to minimize the environmental losses. Next. In Tanzania and Zambia, we tried to target the applications of specific nutrients to the cases where these are required. We used a soil dock testing kit, which is an in-field sort of mobile testing kit. And what we wanted to do is to compare the local recommendations by the Ministry of Agriculture in those environments with what the soil analysis would tell is what is actually required. And that's what we call the soil dock recommendations. And in all the cases, we omitted either potassium or omitted phosphorus because the soil dock test results indicated that was not a necessary nutrient in those areas. And in some cases, we even omitted both P and K. And the results we get show that the yields are similar with the local recommendation for those particular environments. And what this is giving us is that, first of all, the farmer is saving money that would have been used to buy a nutrient that was not required. And it's also helping in terms of environmental safety by not applying nutrients that would end up being leached or lost in the water systems. Next. In the recent years, we have come to appreciate that the continent, and especially sub-Saharan Africa, has high deficiencies of important secondary and micronutrients. And when these are not applied together with the other fertilizers, NP and K, we end up losing productivity and also losing inefficiencies that could be achieved. For specific nutrients such as boron, zinc, we have found that these are either extremely deficient or deficient in most of the cases. Besides, we also see that these nutrients are missing or deficient in multiple cases, so that their occurrences of deficiencies are widespread within the continent. And it's more important for us to address this so that we increase the efficiency in which we achieve nutrient and crop productivity. Next, please. So we have done some work to investigate what extent can we achieve changes in crop productivity by application of secondary and micronutrients beyond what the continent and Sub-Saharan Africa has always done, because most of the work has always been with NP and sometimes NP and K. And the photo on the figure shows there what we have done sometimes, I think in 2016 in Ethiopia. And we observed that the combination of sulfur and zinc gave some very good crop stand that also reflected in very good yield compared to systems where sulfur and zinc were not applied. The bar graph below there is showing us the levels of yields for different crops observed in several countries. This is Ethiopia, Burundi, Mozambique, and Rwanda. And we see the orange part of those bar graphs is what is realized by the application of additional nutrients such as sulfur, zinc, and boron over the NPK. And those yields on average vary between 1 and 2 tons per hectare. This is quite some substantial increase in productivity because of addressing the missing secondary and micronutrients. We also did a meta-analysis, the figure that you see on the right, looking at the studies that have been conducted in sub-Saharan Africa that could be able to provide an indication of secondary and micronutrients effect on the productivity. And what we have seen across all those studies, on average, a 25% increase in productivity is realized. And this is a substantial increase attributable only to secondary and micronutrients over the NP and K yields within the region. Next. Yeah, the use efficiency of these nutrients is actually quite impressive in terms of the secondary and micronutrients. From the work that we have seen is that boron, iron, and copper, for example, result in over 200 kilograms of grain yield per kilogram of nutrients applied. And we see also zinc resulting in 150 kgs and sulfur about 38 kilograms of grain per kilogram of sulfur applied. We also realize that when these nutrients are applied, they often leave some residual effects which would reflect in the yield for the next season, which means that the benefits that these secondary micronutrients bring to the fields are even bigger than what we are able to account for within a season of data. This work is published in a paper that we called Application of Secondary Nutrients and Micronutrients Increases Crop Yields in Sub-Saharan Africa. So you can be able to access it and find out more information on this type of responses. We also wanted to understand the improved efficiency of macronutrients. Next. There is little data available to show us the kind of efficiencies that are achieved when we for the macro nutrients such as phosphorus. And we obtained this data from the work done by 1 Acre Fund, which showed that the phosphorus use efficiency using DAP increased from 198 to 347 when DAP was replaced with a local fertilizer blend called Mavuno that includes other elements that are not included in the DAP. So in terms of the source of the fertilizer, it's important because that determines the use efficiency of the nutrients that we are talking about. Next. Yeah, this one is to summarize the results and the message about the importance of micronutrients and secondary nutrients in productivity. And here, what we show is another cumulative plot, and the level of profits, in this case for the control, the NPK, is the line crossing the X at 0. And what we see is that, for example, for sulfur, zinc, and copper, those are cases where we could be able to get accurate information on the specific nutrients. We see that up to 70, 80+% of the cases observe positive net benefits because of the inclusion of these secondary micronutrients. We also see in the combined case, which the cost will be a little bit higher because that particular treatment contained more than one micronutrient and secondary nutrient, still about 70% of the cases reported positive net benefits of the inclusion of micronutrients. And what we also see is that these benefits are across all the different soil types where the studies have been conducted, except in the vertisols, which are generally rich soils, so that can be expected. Next. Yeah, I have talked about the context in which production is taking place in Sub-Saharan Africa, showing the variations and the landscape positions and the transfers of organic resources and how those influence on the local productivity. We have also talked about the role of fine-tuning recommendations so that we don't apply nutrients that are not necessary in a specific place. And I've now talked about the micronutrients. But I wanted to bring in the kind of response clusters that we observe, or response patterns to fertilizers that we have observed. And in this case, we applied machine learning using K-means clustering to about 250 fields scattered across 4 countries, Kenya, Tanzania, Malawi, and Nigeria. And this is the kind of responses that we got. We see a cluster, the first one, what is written as cluster 1A, which is a cluster of no response. The fertilization, crop fertilization does not lead to increased yields. And this is because of poor fertility. We also see another response category, which is cluster 1B, where response to fertilizers is not observed, but this is because of high fertility in those particular fields. Then we also see another category where we are getting general responses, and especially high response to manure application. And what we have as cluster 3 there are fields that are actually not responding to fertilizers well. There's a very low response, and something needs to be done to boost the responses of this type of fields. And we also observed another type of cluster, which is indicated as cluster 4, which is highly responsive to nitrogen, especially. And this requires that specific type of management are done in such type of fields. We wanted to find out why are these fields behaving this way, and what would require so that one cluster can translate into another type of response. For example, the fields that are poor, fertile, and are not responding, cluster 1A, what can be done to move those to sort of cluster 2 or even cluster 4 to become highly responsive? Next. And what we did was to do some logistic regression across those different clusters. And what I'm showing here is that although phosphorus and, although soil pH, phosphorus, and soil organic carbon are important in determining the type of responses that we get, there are other important parameters such as aluminium, manganese, sulfur, boron, and zinc that, when addressed, can increase the response of a particular category to move into another desired category. And these are nutrients and aspects that need to be addressed for us to be able to improve the productivity in the continent. Next. This is just to show that for those 5 clusters that I've talked about, we have the highly responsive one, which is has 11% of the occurrence, and the non-responsive high production, which is 4% of the cases. And this is only about 15%, leaving another 84% of the cases requiring specific interventions for proper responses to management practices. Next. Now, I want to introduce you long-term trials that CIAT has been conducting, and we implemented this since 2003, and they are ongoing. One of them is on conservation agriculture, involving maize and soybean in different configurations, and the other one is integrated soil fertility management, involving maize and tephrosia, again in different configurations. And all these contain response functions for nitrogen and to some extent for phosphorus. Next. So we have used these trials to understand various aspects, and I want to bring one aspect of greenhouse gases. The photo on the top left shows some chambers for in-field greenhouse gas sampling. And this is work that was being done in the last season that was ending February of this year. We are doing similar work in drylands of Kenya in one site, and we are also doing the same type of analysis in Zimbabwe as we talk. The figure below there, the line graph, is showing nitrous fluxes for specific systems that we tested within one of these long-term trials. In this case, we looked at conservation agriculture versus no conservation agriculture, but we also looked at the control release urea versus the normal urea. And the results I'm showing here are for our work in 2016. What we see is that very similarly to what has been reported for Canada, is that when we plant and apply these resources and there is rainfall, there are peaks in terms of the nitrous emissions. But then this comes down as the rains also subside towards later in the season. But quite interesting for us is that the control release urea, although it showed some slight delay at the beginning, it actually sort of increased in its emissions later on in the season when the other treatments of normal urea had already sort of carved down. So this is an interesting observation. It was only for one season. We would want to have this type of work done for more seasons. And it's very nice to see the advances done in other places with all these enhanced efficient fertilizers that we would want to understand also how they operate or how they function here. The other figures that I am showing there are other assessments of emissions. In terms of environmental losses, we have leaching studies and also erosion studies. Next. So this is summarizing what has been undertaken so far in sub-Saharan Africa in terms of both leaching and greenhouse gases. And we did a very thorough review last year, and then we published it at the beginning of this year, I think around March 2020. And what we see is that there is quite high levels of leaching. Interestingly, there is some cases where the leaching reported by the different authors was a little bit higher than what was applied. But in general, we see that the leaching is positively correlated with the applications of nitrogen. We see the same case for greenhouse gases. Of course, the levels of emissions of nitrous oxides are quite low, as I think has also been reported for Canada. In most of the cases, we are getting no more than 4 kilograms of nitrous N per hectare per year, although in a few cases, this can be elevated. And again, this is related to the level of nitrogen applied in those systems. Next. I want to make my conclusion by saying, yes, it's important for us to understand the context and the drivers of responses in order for us to make for our work in the region. It's important to have strategies to support local recommendations, including landscape variables, tools such as the soil dock test kits, in order to improve the efficiency of fertilizer use. And we have neglected micronutrients for many years, but there is a new interest and a new wave that has come, and this is important and should be an integral part of the 4R work. And we need also to increase our understanding of the environmental costs, because there is not much done. What I have showed you in the last slide is almost all that exists for sub-Saharan Africa in terms of leaching and also greenhouse gas studies. Thank you.
Thank you, Job. Well done. Thank you so much. Very, very, very clear. I hope that people got it the same way. It came very clear to me anyway. I would like to invite Shemi to again do the same. Maybe just a couple of questions, and then we combine with Kaushik because there's some nice overlaps there. Over to you, Shemi.
All right, thanks very much, Ed. Thanks, Job. I want to pick two quick comments, Job. The first one is on the residual effects of micronutrients. The results you show are for single applications. Do we need to apply the micronutrients every year, or they have a long-term residual benefits as well?
Mm-hmm.
Yes, and you could probably combine that with the second question on whether we also observe increased bioavailability of micronutrients in grain nutrient concentrations for improved micronutrient dietary availability.
Thank you, Chami. Micronutrients are similar to macronutrients, where, for example, you don't get residual effects so much of nitrogen. Similarly, some of the secondary micronutrients will have residual effects, but others will not have residual effects because of their mobility in the soil. So some of them, probably like boron, can stay in the soil for some time, but others may not stay in the soil for a very long time. So the residual effect will depend on the particular micronutrients that we are talking about. In terms of the increased bioavailability, I have not done research on bioavailability. The research that I have done that I would actually refer you to is to do with the increased nutrient concentrations in the harvest products. So we published a paper on micronutrients and the hidden hunger. You can Google me and title similar to that, and you're going to get the results that we got. There is increased zinc concentrations. There is high increase in selenium concentrations. There are increases in boron. They are not very significant in some places, but in some places there are some quite significant increases. So the concentration within the grain, yes.
All right, thank you so much. Ed, we'll hand over back to you.
Thank you, thank you. So, I mean, Kaushik, now you have the challenge of being the last man, and we have, I think, 18 minutes or so, and we will depend on you to help us finish on time. Thank you so much. Over to you, Kaushik. Yeah.
Well, I'll try to be as express as possible, Ed. Thank you very much. And also thanks to the organizers for giving me this opportunity to talk about how 4R nutrient stewardship could help balance the economic and environmental priorities in African agriculture. If you could go to the next one, please. I would like to start with a quick review of the realities in African agriculture that basically compels us to think about sustainable intensification and 4R as part of it as critical steps for managing crop production in the continent. Next, please. After a decade of a slowdown in undernourishment, the numbers have started to climb since 2015. And this is important in the context of projected population reaching about 3.8 billion in Africa in 2021. Now, to keep the undernourishment low, far more good quality food and other crops need to be produced. Next, please. This is an example coming from IITA, which says that the cereal production growth rate needs to be quadrupled to keep pace with the increasing population. Next, please. And we will have to produce more under several biophysical constraints. Much of the continental soil are low in plant nutrients and organic matter. A lot of it has to do with the old soils, more weathered soils here. Nutrient depletion is common. As you all know, that lack of fertilizer and manure use is one of the main reasons for that. And about 46 million hectares of arable land, which is about 60% of the arable land, are degraded. And finally, climate change impacts are creating far more complexity and uncertainty in the production systems than we have had before. Next, please. So African agriculture has been, so far, has been driven by bringing more land under cultivation. I mean, if we compare maize and rice areas, it's over 3 times the global average and nearly 5 times of South Asia. How the extent of land, or extensification, I'm calling it, as opposed to intensification. And while the average yields, however, remained about 1/3 of the global and South Asian productivity level. So it's more horizontal expansion than vertical. So next one, please. As opposed to intensification, such extensification basically have contributed largely to the nitrous oxide emissions in Africa. Clearing of wooded land and biomass burning are the major causes. And this is different from what we have seen from the presentation of colleagues from the Canadian colleagues. The contribution from nitrogen fertilizer is comparatively minuscule, in fact, to this biomass burning. And that is very different from several other places in the world. Next, please. Now, one of the prime reasons for low yield in crops is lack of fertilizer nutrient use. The continental average hovers around 15 to 20 kg per hectare, which is about 15% of the world average. So that's one of the biggest challenges we are facing in the continent, and there are several reasons why the fertilizer use is low, but that's a different topic to discuss. Next, please. So it's not really surprising to see that soil nitrogen and soil fertility, which encompasses in this particular study low organic matter and deficiencies of zinc, phosphorus, and potassium, they are coming up as main reasons for yield losses in production systems and the reasons for the yield gap that Dr. Kihara mentioned in his presentation. Next one, please. So basically, the 4R nutrient stewardship, which is applying the right source of nutrients at the right rate, at the right time, and at the right place, basically provides us the guiding principles as part of the sustainable intensification process in African agriculture. Now, all these different R's, the right source, rate, time, etc., each of the rights focus on specific objectives and benefits, but together they help us in sustainable intensification of the production systems that creates economic, social, and environmental benefits to the society through optimized use of plant nutrients. Next one, please. Now I want to move to the next section, which looks at the benefits we have seen in applying 4R on farm in the continent and elsewhere. Next one, please. This the first case study I'm going to talk about is on maize and wheat-based systems in Africa. These systems, 2 systems provide over 70 million tons of grains from about 35 million hectares of land. Average yield is pretty low, which is around 2 tons per hectare. Yield levels are affected by low and imbalanced fertilizer use, weather uncertainties. In most of the cases, the recommendations are blanket, which is for large areas. And we used site-specific fertilizer application based on 4R to identify the benefits of intervention. Next one, please. This example comes from the Tamasa project, where we collaborated with several organizations, including the CGIAR institutes like IITA, CIMIT, the national systems, NGOs, and the fertilizer industry in 3 countries in sub-Saharan Africa. And what I'm going to present in the next slide is basically based on compiled data from a large number of on-farm studies that use the nutrient expert fertilizer decision support tool based on the 4R principles in maize-based systems. Just to touch quickly, that nutrient expert was developed by International Plant Nutrition Institute, which is based on the 4R principles of applying the right nutrients, and there are several of these models available for different crops, and maize is one of them. Next one, please. It's quite a busy slide. What we have seen in this study are that 4R recommendations from the nutrient expert tool basically doubled maize yields as compared to the farmer's practice. And there is a slight yield loss as compared to the farmer regional recommendation and the soil test based recommendation. But what the 4R fertilizer recommendation did was it significantly reduced fertilizer cost and increased profit for farmers as compared to the regional recommendation and the soil test based recommendation. And most importantly, increased fertilizer use efficiency by over 30% as compared to the regional and soil test based recommendations. And this is basically a perfect example of what we are trying to achieve in terms of balancing economic and environmental priorities. Next one, please. We also looked at the impact of 4R recommendations in the irrigated wheat systems in Morocco. Yields and benefits in both the years that are shown here provide ample reasons for adoption of 4R practices by farmers. We increase the yields as well as the profit, and the 2 years, the comparison 2 years, one is a very good year in terms of rainfall, etc. Although the impact is less in the irrigated system, but it is comparatively a better year than the first one. Next one, please. I'll go back to this slide a little later to discuss certain other issues. My second case study is from our work on oil palm. Basically, the map you see here it shows the tropical region of Africa that is a major emitter of greenhouse gases. The yellow tinged area is where you find most of the tree crops like cacao, oil palm, coffee, etc. And cumulatively, this region basically emits over 6 billion tons of carbon dioxide equivalent of GHG. And hotspots could emit over 4 tons per hectare per year of CO2 equivalent. So sustainable intensification is critical in this region from an environmental perspective, but also important as smallholder farmers operate in this region. Next one, please. We worked on oil palm in Ghana with commercial plantations and smallholder farmers. Ghana is a major producer of oil palm, and but the production or yield remains stagnant over the period, even reduced over the last decade, while the area and the production improved. So basically what happened is more areas came under oil palm, and obviously that came from clearing of more wooded area, and one of the main reasons for GHG emission that I've showed in the beginning. Next one, please. Smallholder farmers cover over 90% of the oil palm area and contribute about 80% of the country yield of oil palm in Ghana. But the smallholder farm yields are less than 1/3 of the commercial plantations. So our interest in oil palm intensification is for its multiple benefits. First of all, yield improvement and profitability improvement, and then reduced emission and increased carbon sequestration, and providing a compelling case against extensification, which is what we are trying to do in Ghana. Next one, please. Actually, I wanted to elaborate a little bit about the 4R in application in tree crops, because there are not too many studies on 4R application in tree crops, so although it's true for all crops, but crop-based management practices must go hand in hand to accrue the best benefits of 4R application. And this is very true for the tree crops, particularly in case of oil palm. The pruning, better frond management, clearing up the root zone, etc., are some of the best management practices for crop-based management practices. In the experimental field, what we did was we layered 4R over the crop BMPs and estimated the rights for each site, sourced by use of soil and foliar testing, rate based on yield targets and soil nutrient supply, applied the nutrients 3 times per year during the rainy season, which is the best practice, and broadcasted the fertilizer in the root zone. Next one, please. The outcomes in the smallholder farms, the major contributors of oil palm production in Ghana, as I mentioned earlier, are quite promising. We could increase yield and farm profit by over 4 times, but along with that, above and below ground carbon stock were increased, making a good balance of economic and environmental outcomes. Next one, please. My third example is from Asia. Actually, I thought that it would be important for the audience to see some study outcomes from the smallholder systems of Asia, where 4R application and adoption are well advanced as compared to Africa. I point you to some selected studies, and I've given the links at the bottom of the table, which you can go back to later, where the authors estimated multiple benefits of 4R application, spanning from increased yield and profitability, reduced greenhouse gas emission and global warming potential, increased nutrient use efficiency and carbon sequestration. And these studies provide us with ample evidence that potential benefits from 4R application in complex smallholder systems like Asia and Africa are pretty high. I want to focus on scaling in the next section. Next one, please. Next section, until and unless 4R is amply disseminated within production systems, the benefits will be limited. So providing farmers with usable knowledge on 4R in the complex smallholder settings is probably the most important and also difficult part of the 4R research to development process. Next one, please. Yes. Our Chinese colleagues of IPNI did assess the impact of 4R in cereal production in China. This is basically looking at business as usual versus 4R practices from nearly 17,000 field trials, showing that projecting that application of 4R in the total acreage under rice, wheat, and maize would produce high gains. Like there would be more than 30 million, excuse me for a second. It's about 300 million tons of extra production, significant reduction in nitrogen use and loss of reactive nitrogen, carbon dioxide equivalent emission is reduced significantly, and the profitability went up significantly. So high monetary profit, basically. Next one, please. Yeah, we now switch to Western Kenya, where APNI, the African Plant Nutrition Institute, is working with smallholder farmers to promote 4R in several crops. As you can see that it's quite self-explanatory and basically echoes the Chinese estimation that 4R application increased yield significantly over current yields of several crops, and that led to higher benefits for the farmers and potential reduction in GHG emission. Next one, please. Over to the North African wheat system, where we used farm surveys before and after 4R program implementation to basically assess the adoption of practices. And I present here with results from the rain-fed as well as the irrigated wheat production regions of Morocco. As you can see that between 2014 and 17, farmers started switching to NPK fertilizer sources from a predominantly NP fertilizer use. The use of nutrient potassium picked up, while nitrogen application particularly went down in the irrigated region where wheat, particularly the wheat and sweet potato cropping systems are followed. And the use of combined seed cum fertilizer drill went up as farmers became aware of benefits of fertilizer placement. In the next slide, I briefly summarize the process that we followed to initiate change on the ground. Next one, please. As you can see that, now the previous one. Yeah, so it basically shows you that initially the 4R scientific knowledges are developed and methods developed, extension capacity locally were developed, yield and economic performance of standard 4R practices were evaluated and shown to people. Household and farm level data used for coming up with site specific or farm specific recommendation. For materials developed for use at different levels like research, extension and farmers level. And finally, for our principles and practices mainstreamed, working actively with government, private sector, NGOs, and advanced research institutes for implementing the intensification program. Next one, please. And the benefits that we have seen, this has supported regional governments to revise fertilizer recommendations for our learning sites, which we use very frequently, is adopted by the county governments in different parts of the continent. For our practices and approaches are adopted by AGRA, 1 Acre Fund, several CGIAR institutes, local fertilizer companies, so that it spreads out to more farmers and benefits, the overall benefits are multiplied. So I want to conclude by saying thanks to the organizers. I also wanted to let the audience know that with the generous support from Global Affairs Canada, APNI is supporting Fertilizer Canada and Cooperative Development Foundation Canada to implement a 4R program in Ethiopia, Ghana, and Senegal that is expected to impact the livelihood of more than 80,000 smallholder farmers in those targeted countries. So I thank you for your patience. Thank you, organizers, and I would be happy to answer any questions, or you might send us an email to know more about our programs. Thank you very much. Over to you, Ed.
Thank you so much, Kaushik. That was high speed, but still the pace was still understandable and very clear. Thank you so much. Sorry about the pressure that as a last speaker you had to go through. But we hope that we can get some minutes in here and get some questions answered. And for that, I would like to go back to Shemi. Shemi, are you ready?
Yes, Ed.
Let's use the minutes we have, yes.
We want to start with two questions. They are very interconnected that Kaushik could address together. The first one is asking for specific details on what are the components of the 4Rs that are normally missing in the farmer practice regime, and how we identify the opportunities for improving on what the farmers are doing, and come up with what we can consider to be an appropriate 4R package. And then the second question is in relation to 4R, yes, a big emphasis on the right time. And the question is there any relationship between growth stages and the time of nutrient application? And I'm sure that could pertain to various crops.
You want me to answer that, Shemi?
Yes, so you could tackle the two questions together.
Okay. Well, with my experience in Asia and Africa, the most important thing that is missing in farmers' practices are rate and time. Rate in the sense that it's usually not adequate. In case of unavailability of sources often drives the imbalance. And application timing differs significantly from the way a particular system requires you to apply. And so rate and timing is something you can really make a difference. In terms of source, you are often challenged by what fertilizer is available in that particular location during the cropping season. So these are the two things, that rate and time, I'd flag as the two most important. About timing, obviously, timing is very closely associated with the nutrient uptake. And there are, for each of the crops that we deal with, there are very well-researched timing when the rapid uptake starts and to a certain point. And obviously applying the nutrient during that time gives very little time for the nutrient to sit on the soil, and the potentiality of loss is limited. So definitely the timing is well aligned with the uptake pattern of the crop.
Thank you so much. John, could you, I want to just bring you back, to provide, an answer on a very specific question on whether polymer-coated fertilizers are available in Ghana. You may also give an overall point of view from Africa in general.
Yeah, thanks, Shami. I think one of the important developments in sub-Saharan Africa over the last probably 3-4 years is the high penetration by the fertilizer industry with various products. The product that we have used, the controlled release fertilizer, which is of course polymer coated here, was supplied by a company which is operating in Kenya. It's called the ICL. And I believe there are companies operating in different parts. We have been meeting with them in some of the forums, Shami. So I guess it's just a matter of trying to find out who are those suppliers that could be in Ghana. I don't know about Ghana, I know about West Africa.
All right, thank you very much, Job. So Ed, I think that covers the questions that we wanted to discuss, and I will hand back over to you. There's a question on the accessibility of the presentation, after the webinar. I'll leave that to Clyde for the closing to provide an overview of how the participants will be able to access the presentations after the meeting.
Thank you so much, Shemi. As usual, did justice to making sure the key questions were identified, and where possible, they were weaved together nicely to allow discussion. Again, sorry that we had that small hitch where we lost a few minutes, but I think we have done a good recovery. I think we were able to recover both in terms of getting back quality slides, but also being able to finish all the four without somebody feeling like they didn't have enough time to finish. So before I hand over to Clyde, I just want to, from where I sit, some of the things that hit me as I listened. One of them, I won't get into details because of time, but one of them was what I would call the context differences between Canada and Africa that provides very great learning opportunity. And the context differences that I was listening to relate both to technology differences, but also the context around biophysical contexts between Africa and Canada. And that in fact, we can learn from each other significantly. Africa can learn from Canada and vice versa in terms of what's possible. I also saw that, best practices, particularly the African presentations, mentioning that the fact that best management practices have a role to play or have great potential to reduce GHG emissions. And that we should flag that as something worth looking at. Macro as well as micronutrient studies in Africa, I think Job's presentation gave some light on that. Very little work has been done on micro in particular. And I think there was some very interesting lines that we got shared. The question about residual carryover effects of micronutrients was raised, not much discussion yet, but clearly that's an area that perhaps require going forward that we look at that. The last bit of Kaushik's presentation about scaling of forward in Africa, I think is a big interest area. I mean, and perhaps one of the big objectives of this collaboration is that how can we help the 4R stewardship to be in more places and to be done in a deeper and more meaningful ways, taking into account the context differences that we recognize exist. And I think finally, I really liked that answer about from the 4 R's, which ones are the most challenging for smallholders? Oh, most definitely rate and time, the biggest ones. Farmers hardly have the resources to get the right rates, even where they know what the right rate should be. Time is not in their hands because of access, availability, and all that. So I think in thinking about priorities, working with smallholders, emphasis on how can those be addressed or be helped along would be really, really important. I would like to leave it there. There are some very interesting points that have come out, but I think we have to leave it there. And at this point, I would like to hand over back to Clyde. Perhaps he will also comment on the slide deck availability and the whole issue of questions that may be posted online. Over to you, Clyde.
Well, thanks very much, Ed. I think that was an excellent summary, and thanks to all the presenters and to Shamie for fielding the questions.
Yes.
So we are definitely interested in your feedback from the presentation today. If you have questions that you felt weren't answered, please send them by email to us. All the questions that have been posed during the session online and anything we receive afterwards, we will respond to on our website. My personal perspective would be that I think in Africa sometimes there's a tremendous focus when it comes to climate change and greenhouse gas on resilience and on adaptation. But I think we've had a good discussion today on mitigation. If Africa is going to improve its productivity in crop production, there is going to be more fertilizer used. And as fertilizer use increases, there will be increases in greenhouse gas emissions from agriculture. I think what we have, though, is an opportunity to limit the growth of those emissions by using 4R nutrient stewardship. And I think that that's where there's common cause between Canada and Africa in terms of the science of greenhouse gas emissions. I want to invite everyone to attend our next webinar on the 4Rs and precision agriculture, which will be focused on nutrient sources. We had, I think, a really good taste of that from Job today, but I think we will hone in on the nutrient sources in a more detailed way at the next seminar, which will be Monday, September 14th, 8 a.m. to 10 a.m. Eastern Time. So please keep an eye on our website for the registration information for that next session. As I said, all the webinar materials, the recording, the presentation, the Q's and A's, speaker bios are all going to be, are all uploaded on our website at 4rsolution.org for our webinars. We also have a champions program. We'd like more people to get engaged in that, where we have grants available for our micro projects in sub-Saharan Africa through our Forest Solution project. And again, that's on the website. We'd encourage some of you to see if that's of interest. And then generally, you can also get access to our newsletter and other information about the 4R Solution project through our website as well. So I think that's all I've had for today. I appreciate people sticking with us if we've gone a little bit over time, but it was important to get some extra questions in. And hopefully we will see you all on September 14th at 8 a.m. Eastern Time. Thanks very much, everyone.